So in this video we're going to review direct proof and how you do a proof, mathematical proof, if you want to do a direct proof. So remember, at the start of the term we looked at truth tables, and in particular we looked at the truth table for the implication P implies Q. So remember, P implies Q means if P then Q. So in a direct proof, what we want to do is take an implication, if P then Q, and prove that that implication is true. And the way that we do it is simply we look at the truth table for P implies Q, and we say, when is P implies Q true? Well, P implies Q is always true if P is false. So if we want to prove that P implies Q is true, we don't need to worry about the truth value of P. We do know that if P is true and Q is false, we get a false statement. So what we do in a direct proof is we assume that P is true, and we show that if P is true, Q must be true. And if P is true implies that Q must be true, then we get a true statement. And if it's the case that P true implies Q cannot be false, if P true means that Q can't be false, then we don't have to worry about the second row of the truth table happening, and we wind up with a truth table that has only true values in it for the implication P implies Q. So the basic technique is, for direct proof, assume P is true, that's step one, and then we show if P is true, Q must be true. And if we can do this, then we prove that the implication will always be true. So here's a simple example. We have an implication, if n is odd, then n squared is odd. So in this case, our P is the proposition n is odd, and our Q is the proposition n squared is odd. And for a direct proof, which is what we're doing, we assume that the statement P is true. So if P is true, that means that n is an odd integer. And what we want to show is that if n is odd, n squared must also be odd. So when you do a direct proof, we'll start off by telling the reader that we're ready to do our proof, and we'll tell the reader what type of proof we're going to do. We're going to say, hey, we're going to do a direct proof. And when we tell the reader that we're doing a direct proof, they know that we're going to assume that P is true. In this case, they know that we're going to assume that n is an odd integer. So we want to start by making that assumption. So we'll say, suppose n is odd. Then we need to do something with that. We need to think about, what does it mean to be an odd number? Well, to be an odd number, we know that when you divide an odd number by 2, you get a remainder of 1. So we're going to rewrite n in that form. So suppose n is odd. So it follows. So something follows from the fact that n is an odd integer. It follows that n is an integer multiple of 2 plus 1. In other words, n can be divided by 2 with a remainder of 1 because n is an odd number. And so n is going to look like 2k plus 1, where k must be some integer. So we supposed n was odd. We indicated what that meant n had to look like, and now we're going to do a little bit of math with that. So I'm going to say it follows. Some math is going to follow from this. It follows that n squared, we're trying to show that if n is odd, n squared must be odd. So let's do something with n squared now. N squared, what does he look like? Well, if n is equal to 2k plus 1, then n squared is going to look like 2k plus 1 squared. And what we want to demonstrate is that n squared will have a remainder of 1 after division by 2. That will prove that n squared is odd. So we just work this out. 2k plus 1 squared, we'll square 2k plus 1. That's going to give us a 4k squared plus 2k twice, so plus 4k, plus 1 times 1 is going to be 1, equals, and now I'm going to group these first two terms. I'm going to say equals 2 times 2k squared plus 2k plus 1. And now I want to notice that this has the form of an odd integer. It's 2 times an integer plus 1. So this is a form that would have a remainder of 1 after division by 2. So I'm going to say equals 2 times some integer k sub 2 plus 1, where k sub 2 is just the 2k squared plus 2k stuff that's an integer. So this form, 2k sub 2 plus 1, is the form that an odd integer would have. So now I'm going to conclude that n squared is an odd integer because its remainder is 1 after division by 2. So this implies, this result right here implies, what does it imply? It implies that n squared is odd, as desired. That's what we wanted to show. We wanted to show that if n was odd, n squared was odd. That proves the implication. So we end the proof now. QED, that which was to be demonstrated.